Okay, good evening. My name's Mark. I work for Microsoft. I've worked for Microsoft for about 18 years. I am British, but I've lived in the USA for 18 years. I've worked on Azure for about 9 years, and I've seen Azure grow from like nothing to what it is today. And hopefully what I want you to take away from this thing is some appreciation of a couple of the services that we've built inside Azure and sort of the design decisions that we made and how we built them, and how we took ourselves down really a path of where we had a bunch of box products, well, at least one of them's a box product, and then turned them into services and what that meant. And so I really kind of want to give you a chance to ask questions. I love it when people ask questions as I go. I've been told if you ask a question, I'm going to repeat the question so it gets recorded. And then at the end, we'll have a chance to ask more questions then, if you want. So just ask questions as we go. So the goal of this talk effectively is for you just to kind of give an appreciation of sort of one of the things we've done inside Azure. And if you want to take it off topic to some of these things as well, feel free. Anything's game in terms of asking me a question. I'll just do my best to answer it all. So just give you a little bit of background before I dive into the actual use cases. Azure is a bunch of regions around the world. There's 50 of them now, apparently. This isn't most up to date in terms of all of the regions, but they're all over the place. And for each week, there seems to be a new region that pops up as we spend a lot of money on building these things out. And we build a lot of the services inside those regions or the microservices concept. Not everything is built that way. Some of the older services were built on a technology we built called cloud services, which I wouldn't necessarily class as a sort of microservices approach, but it's sort of getting there. It certainly had the concept of deployments and scale out, but the agility wasn't really there. Scaling out some new services took time, and the density wasn't really there when you built it on cloud services, if you know that technology. But all of these ones are, and they have a variety of services here, not just built inside Azure, but outside Azure as well. Some of them inside Office. Sometimes Cortana runs inside the Bing data centers. Skype runs inside Office data centers. So these are kind of some of the ones that we've built recently over the years. And I'm going to zoom in on a couple of these. We also have a lot of core Azure services as well. So a lot of the platform services, like when you phone up and do incident management, or the monitoring service that you see inside the portal, and it gathers all the monitoring from your services. We have security services. We have network stacks, and a lot of the core Azure services are also built with a sort of a microservices concept now. And so, this is pretty much the paradigm of how we build things inside Azure. As you guys are probably very aware, typically it used to be a sort of you can build a lot of applications with a tiered structure, where the traditional approach was certainly when you had your box products that we sold was you take some machines and you build a set of processes you deploy across those set of machines where you have your middle tier, your front end, your back end tiers, and everyone sort of knew what the machines actually did. And you pointed it and went, oh, there's my database machine, and these are my middle tier machines. With the sort of the microservices approach, it's much more about clustering. You build clusters of things. You have scaled out machines, clusters that you scale out. The clusters are very heterogeneous. They can consist of all sorts of different types of machines. And of course, you deploy smaller pieces of code. And you do that because of a sense of agility and because you need scale out on those machines. And also, what we found was it was much, much harder to actually manage the services than it was actually to build the services. So management of doing rolling upgrades, deployments, versioning, failover, and all that side of things took kind of years to get right. So really, this was all about building services and how you do those. And with an N-tier structure of things, you don't really build services around that. You kind of sort of build up to a certain scale. But when you want to build a scale of the services that we run at Microsoft, which is thousands of machines and across clusters in those regions, we had to have a platform that could deal with all of this and an approach to deal with all of this. So basically, we built out the concept of clustering. The clustering technology we built on is not anything to do with Windows Server clustering, if you know that technology. That thing we discovered a long time ago could only scale to about 100 or so machines at best. They stretched it to about 120 at one point. So we built a whole bunch of new clustering technology. So the clustering technology scales to thousands of machines. It's actually unlimited. We've scaled the clusters up to 10,000 machines in size. And at that point, there is no limit around those things. So This clustering technology is kind of pretty rich in terms of how you do that. So a cluster really defines itself as it takes a set of VMs. You deploy the platform on top of all that. The platform itself spins up this cluster that you can use any types of the VMs inside it all. So we can use machines that are all of different heterogeneous sizes. You typically expose the cluster out through the Azure Load Balancer, and then effectively you attach to the load balancer and do whatever you want to talk to inside the cluster. So that's the concept of a cluster. So what I'm going to do is look at it the eyes of two services. If you're familiar with these, Event Hub is very topical, given our queuing discussion just now with RabbitMQ and Kafka. So we'll talk about Event Hub as one of them, and then I'm going to also talk about Azure Databases. And Azure Databases actually is a very interesting service because it was one of the first services that actually we took to turn our box products into the cloud. And we had a project back in 2007 called CloudDB, which is how we did that and spawned many of the technologies which we subsequently built the rest of our Azure services on top of. But I'm going to dive into Event Hub. Event Hub, what it is it's sort of a big fat pipe of stuff. The scenario is effectively you used to have all this sort of kind of multiple interconnection between things, but instead you can stick this big fat pipe and you can actually use it as a message queue where you can effectively store all your messages in terms of, from one particular device, from what your publishers are to what your consumers are. So, the way it works is you spin up a thing called an Azure Event Hub. You have a set of partitioned services inside here, which are things that are queues where you hold all your message data. You have a set of event producers. They pump messages in, either over the MQQ protocol or over HTTP protocol, and you basically fill up all your message partitions inside here. You can then define a set of event receivers. They can get defined into a collection of groups called consumer groups, and then they read from any of these partitions from any of the collections that you want. So, the idea here now is it's a big pipe ingestion for whether you're sending telemetry data or you're kind of gathering diagnostics from IoT devices, and anywhere else you have data that's coming in that you want to run at sort of high scale throughput through these partition services, through this message queue effectively. And you can partition this whole Event Hub out. You can start with like one partition, and you can scale out any number of end partitions, and you can have any number of consumer groups on top of it all. So that's effectively what the service does. This is built within one of the teams that I work with. So we've sort of designed it over the years. I'm not actually responsible for Event Hubs in any way. I'm responsible for the platform that this thing builds on top of. But it's a good example of the types of services that we build. Anyone got any questions at this point? Yes? You're going to have to say that a bit louder. Yes? It is. So the question is this AMQ, when you say MQ agent, the AMQP protocol? Yeah, I think it's fully AMQP compatible as terms of that protocol is, yes. They recently as well put on top of this as well as a Kafka endpoint as well. So you can actually do Kafka into this as well. In fact, they just released that. So it supports other protocols on top of this. If that's the way you want to put it, yes. And you can produce other consumer groups around this all. So let's sort of dive into this a little bit more. So the way this works is the unit of deployment is a cluster. You go into each region and set up clusters in those regions. Clusters are shared nothing architectures, so the clustering has no dependencies on external stores. A cluster is a fully isolated, independent thing. It has its own storage technology. It has its own independence of it, or you can scale that cluster out. And you can scale the cluster from 3 machines up to 30 machines, up to 3,000 machines, whatever size you want. Typically, the event-head clusters are around 70 to 80 machines in size. We build out clusters on every number of clusters per region. We put customers and pack those into that particular cluster. When it gets full in terms of the capacity, and that means the usage of it is around about 70, 80% in terms of utilization, we sort of say that one's full, we build out another one, and we kind of start filling that one up. We watch the clusters that are currently sealed. If they have demand that scales out, we add a couple of machines to them all. If the demand goes down, we take a little bit of the machines out. It's all kind of a cost optimization thing to try and make as much money as you can by running the machines and making sure the clusters are most efficiently used. There are clusters that are multi-tenant, where many, many customers use that same cluster. And there are some customers that you can buy, and you can have your own dedicated, effectively, cluster that you want just for all your Event Hub workloads inside that. And that's called a dedicated SKU around those things. So that's kind of pretty straightforward in terms of what the underlying clusters look like and how they get managed. There's around about 250 of these clusters. We add about 10 to 15 per month. And the total throughput of all the clusters is around about 25 million events per second. And so in total, they're consuming about 2.5 billion events per day going through all of the traffic through all of these clusters. And I think I've been told that the transactions per month are in the trillions in terms of the throughput across all these clusters in all of these regions. So let's then dive into what the actual design of what those clusters look like. So generally, the clusters consist of two types of machine types. We have machines that host front ends and ones that host the back ends. The front end machines tend to be smaller capacity because they're just doing simple routing around them all. And the back end machines tend to hold a greater capacity in terms of the actual Event Hub processing services. So these are sort of actually the clusters. And so the machine sizes, although I put 3 here, typically they have maybe 4 or 5 gateway-defined machines, and then there's maybe 50 or 60 of the back-end machines. But you really want to look at what's running on the machines is what's important, because those are just the physical machines. So what's actually running on the machines is we build microservices around these things, and on the front-end machines, we build a microservice for a gateway. And this really is the ingestion of all the data. I'll dive into what that gateway process does effectively. But it's taking all the data, and it's a shared service. So basically, all the requests coming into this particular cluster are sent through a bunch of gateway services. And the Azure Load Balancer just round robins across all the gateway services. So we refer to these things as sort of stateless. They're just holding everything in memory. And in the case of the gateway services, they persist any state off to SQL. And then in the back end, we actually spin up instances for each of the actual queues, the partition queues that you saw, that hold all the data on a per customer basis. So when a new customer comes along and goes, I want an Event Hub, we spin up an instance of any number of those services, and it's a scaled out number of instances. So if they say, I just want 2 partitions, they'll just get a couple of instances. If they want 30 partitions, they'll get more instances of it. And so every time a customer asks for an Event Hub, we spin up more instances and start packing these onto the back-end machines as efficiently as we possibly can. So that's kind of the general design. You've got shared front-end gateway services, customer-specific back-end services, and then the gateway services effectively are about how do they route all the messages to the right back-end service. So let's look at the gateway service and what it does. The gateway service is responsible for effectively doing receiving all the traffic from the Azure Load Balancer. You're pushing it into the Event Hub service. And it's particularly looking at security. Are you allowed to access this service in the first place? It does a lot about connection management. We get a lot of people who try and abuse the service and pile thousands of requests, and they only have a certain amount of limit in terms of the capacity. So we start rejecting connections. And of course, once we start looking at all the traffic, it looks at where the traffic is supposed to be routed to, and it starts routing it to the particular customer instance. So it has metadata tables, effectively, of how to route that traffic. And it takes advantage, effectively, of the platform capabilities to route wherever that particular customer instance is running. So if you can imagine at the back-end service where the customer instance is running, it's on some machine somewhere. You don't know exactly where it is. The gateway service looks up and does the routing mechanism to the right instance of the service running in the back end. And it pushes all its state into SQL, but for efficiency reasons, actually dynamically, we hold all of the state on a persisted state store across the actual physical machines as well, because you pretty much find that when you start building these services, you become obsessed with latency between these things. We built a lot into the platform to reduce latency and throughput. And so it's fine writing out all this state to a backend SQL store, but cached local persistence data is important. And then that effectively is where it looks at all the metadata for how it looks at any particular customer instance and how it routes those to the backend. The other thing that you have to think of a lot about when you start building these services is how you do your rolling upgrades and your high availability across these clusters. So if any particular machine fails, in the case of a stateless gateway like this, it really isn't that difficult because it just picks up the load elsewhere. But we will spin up new instances of the gateway service on available machines. And often you sort of may have to push some updates across the actual service instance so you can do a rolling upgrade across those. So the platform it builds on allows you to do a rolling upgrade of pushing out new code across the instances of the gateway. The gateway service actually is fairly tight. The way it works is it's fairly tightly integrated with the Azure load balancer. So when you do your rolling upgrade, the first thing it does is it pushes back on the Azure load balancer with what's called a health probe saying, don't send me any more data, lets it drain all those instances of that. And then when it's drained all the instances of that, it then kicks off the rolling upgrade so it doesn't leave these hanging requests where the Azure load balancer sends it to an instance of the service on a machine that's no longer there. So there's some coordination activities between the actual gateway service pushing back on the load balancer so that ingestion traffic doesn't get sent to it all. And then it's responsible effectively for figuring out where to send these to the backend service where you have a particular customer instance running. When you look at the backend, there are kind of three big technical challenges that you have to face of how you run the backend service. How you can pack the density for cost efficiency on those set of machines, how you deal with failures, and then the general resource utilization, given the fact that some customers' instance of their event hub can be using, can be pushing millions of events through it all, and another one could be kind of just having completely idle, and they're not using any form of traffic whatsoever. So they vary enormously across the traffic that you get through these things. And you have to be able to figure out what's the best way of you taking the best utilization of your available resources. So you have to imagine you have this pool of machines and you're trying to push it to the maximum capacity you can, because that way you get the maximum cost around all these things. So these are sort of the hardest problems you had to solve around it. The state for all of the back-end services, actually I'll dive into where the state gets stored, but it all gets pushed into a state store as well, although to a large extent, the state of the actual messages themselves are held in memory as much as possible for low latency reads across all of those, and then they're batched into blob storage for disaster recovery. But let's look at the efficiency around these things. So what happens inside event hubs is that every service is mapped to what we call a partitioned microservice. And effectively what that means is that when you build out, you say for your event hub and you want each one of those partitions, every one of those runs as an individual microservice for each one of those partitions. And it goes to quite a high density. Many people think that containers is a way of deployment for microservices. Very few of the services inside Azure actually run inside containers. Most of them just run inside processes. And then quite a lot of the microservices, actually examples like Event Hub, pack multiple microservices in at the process level as well. So you can actually run tens or even hundreds of microservices inside an individual process itself, each one of them individually tracked for how they can get upgraded. That's exactly what Event Hub does. It has a number of different processes. It launches partitioned microservices as just pieces of code that run inside those. And each one of those is guaranteed to have one and only one instance of that partition running at any one time. So that means, and we'll talk about failures in a bit and how we handle all those failures. So the platform effectively deals with how when you have a failure and you have an instance of that microservice running, it'll guarantee that you won't have one, when you spin one up, it will guarantee that there aren't two instances running up in two places, which may have two copies of your queue, but you'll only have to spin up a single instance of this service again, which has the single queue that it has before, so that we know what to do all the reads from. And then the platform also takes care effectively of making sure that when the requests come into the gateway asks the underlying platform, where should I send this thing to? And so customer A might be on this machine, customer B might be on that machine, and the event of failure, of course, that all got switched around. So there's this strong guarantees in the platform where there's only a single instance of a service running. It runs on only a particular machine, and it's always known to the underlying platform where that is, and then the gateway that sends in requests because know where to send forward that request to. And then the state of all of those backend services are the partition messages are pushed inside blob storage, where it keeps them as persistent state. But they're actually also held all in memory. Actually, I'll talk about that in a bit. So then the other hard problem you have to deal with is when machines fail. And what that means is, a machine goes bad. You have to figure out what was running on that machine. You have to detect failures very fast. The underlying platform can actually detect a machine failing in around between 2 and 5 seconds in terms of it's actually no longer physically there. That turns out to be one of the harder problems inside clustering, and then figuring out what was running it. And of course, then it makes a decision about the fact that it's got to place those things in another running instance of a VM in the most efficient way. So, the idea is to move them to the machine that has the least capacity. So detecting failures and moving failed instances, or recreating new instances, I should say, and then loading up their state again so that they can recover from where they were. And there's single instances of them running on the machine is kind of part of the guarantees. The other thing that you get is that there's a dramatic difference in terms of the usage across different event hubs inside the system. And so that turns into this capacity utilization problem about resource balancing, where you might have one machine that has 2 event hubs that are running very hot, and another machine where they're not running very hot. And how do you deal with all this? Well, it turns out that in the platform that we built for this is that you can report a metric for some level of capacity, whatever that is. And in terms of what event hubs do is they report the capacity of the queue size of the amount of data and the processing on those things. And so every partition is reporting their queue size up. You get an underlying indication of how much resource that particular event hub is requiring in terms of in-memory resource to store the queues, as well as the work it's doing to save that to the state store, the blob storage. And that all gets reported so that you can have this event hub queue requires this amount of utilization, and this event hub hardly has anything. And so now you've got this complex problem of how you do the efficient packing around them all. So the platform really takes all this load information, and every 2 to 5 seconds, it's running a load optimization algorithm about those resources. And then if a particular machine gets hot and the capacity is inside it, it starts to move those back-end services off onto other machines and pack the density for the event hubs that aren't, microservices that aren't particularly highly used onto one machine. But if one of the machines is running hot, it gives it more capacity. So all of this resource management and how it does the reconfiguration of the set of services. So don't forget, across this 50 machine cluster, you've probably got around 20 or 30,000 services running across that. And you're trying to most effectively partition and pack the density of those services within inside this cluster. So that's kind of one of the hard problems that the platform solves. But it actually turns out very easy for the Event Hub guys to build their service, because they just report a particular piece of load, and the underlying platform does all of the calculations and the optimizations around how those things run. Any questions at this point? Yes? Oh, so the stream is stored in, so the stream, yeah, so good question. So there's two, I was talking about 2 different services. So the gateway service, in terms of the routing rules and where the customers are and how to route things, stores all of its state actually inside SQL for disaster recovery inside those. The state of the queue itself, in terms of the messages, is actually all pushed into a blob storage queue. So blob storage is like a binary blob storage state inside Azure that you can use. But for efficiency reasons, actually, everything is actually held in memory. So actually, this is my next slide, this slide here. So the state of the actual queue itself, there's a huge disparity between a number of reads and a number of writes. So you get a 300 to 1 ratio in terms of reads. So the actual state of all of the queue itself is actually held in memory and then periodically batched and written out into blob storage for disaster recovery. And so you get so a request comes in and you build up a number of requests in memory, batch them all up, push them out to blob queue. And then when reads come in, they're actually all read from memory and served out to the client. And then that whole thing, the way Event Hub works is it's a time-based algorithm. So after a week or some periodic time you have, it starts dropping all of the stuff out of memory and out of blob storage in terms of that. And then it actually does optimize the memory usage it keeps depending on the last 500 reads that you did. So that's the way the actual backend service works in terms of the read efficiency operations inside that. Does that answer your question?
Yeah, yeah.
Okay. Going back to the resource one. Oh, yes, we have another question.
You mentioned that you restore, when a machine goes down, you restore the state of the microservice from where it left off.
Yes.
Is that state consistent with the state of the queue that it gets back? Or is it not guaranteed to be?
It's, in the case of event hubs, it's not fully consistent. There is because they batch it into 20 batches before they write it, there is a window of time where you will lose some period of those batches. So they don't provide fully consistent guarantees. Other services do. In fact, the platform it builds on does provide full consistency guarantees if you want to do that. So there's sort of they chose to build a service with non-consistent guarantees around this all, and there is a window of time where you will lose actually of these things. But they consider this as a pipeline of kind of data telemetry as the main scenario. If there's actually another service called Service Bus that does provide full consistent guarantees over delivery of the messages. Yes?
The resource balance you described is very similar to Apache Mesos or Kubernetes on the systems.
Yeah. Well, let me give you a little bit more about the resource balancing. So this is just a graph from the Event Hub for a Halo 5 server where they were sending a whole bunch of telemetry on the usage of the actual machine, the players. There was some telemetry from Halo. It wasn't actually the playing of the game, but when the machine, in-game, as it was running, they were pushing the telemetry around about how the game was being played. So you can see that they had an 18-machine cluster. They had 200 partition microservices. And you can see that so each one of those colored graphs is effectively, as the number of requests go up, how they distribute the load across a set of machines. And you'll see that as each one of them gets hot, it actually kind of, there's this graph basically of the number of requests and the distribution of the microservices across each one of the machines. And you'll see that it's more or less consistent. There isn't one machine that's hotter than another machine or has more services running on it, or they're all roughly about the same depending on how they're running. Yes?
How do you stop feedback loops? So say you saw one hot server cluster and one not so hot, and you started to back it round. How do you stop it creating multiple loops?
Yeah,
so looks like a loop.
So the question is how do you stop this sort of kind of? Yes, you actually have there's actually a configuration thing called that's like hysteresis. It's like how frequently do you move this thing around or not? There's a thing called capacity metric. Isn't it capacity metric? Which defines the amount of time it takes before you will move this thing again in terms of moving it back to another machine. Yeah. Actually, Vlad will kind of answer some of these things. So the actual load balancer has a number of metrics inside it all. There's thresholds that if you'll hit, whether you'll make that decision to move. There's thresholds in terms of how frequently you move it around. Yeah. So there's large numbers of optimization. So what we've done over the years is we've taken, actually Azure Databases, which I'm going to get onto next, is one of the services where we've taken a vast amount of telemetry data from. But we've optimized all these algorithms over the years of how the data moves around for our load balancing algorithms, for the distribution around these. And it kind of, you kind of sort of can tweak your service over time around these things, but it's sort of, you can find there's a large, well, there's a Actually, I'll point you to a paper. I'll point you to the paper that actually describes this, because otherwise I could go on for too long time about how it works without, I'll point to a paper that exactly tells you how this works. But the interesting thing is that you see these graphs around these of different workloads. So this is from Halo. If you're going to see a graph from, there was an education company called Janison that they spun all their clusters up for telemetry. They do nationwide testing in Australia. And so they have a week graph. So you see that on a Sunday and a Monday it goes flat, and then on a Monday spin it up again. And you'll see it kind of peak out on the Monday around there and go flat again. So we can see these graphs, and we often go in and look at the event hubs for different customers to see their cyclic activity and what it all looks like. So they're all very unique in their structure, actually, in terms of how they run. But the Halo one was kind of quite interesting. I talked about the sort of back-end service that's storing its state, and that's pretty much it for event hubs. In terms of how they build theirs. Theirs is, so there was a lot of complex problems solved by the platform, but for the actual Event Hub team, it wasn't too hard a problem about how they built these things, because the platform took care of many of the difficult problems in terms of failover, load balance, resource balancing, and discovery of where things run. Let me talk about Azure Databases for a while here now and dive into this service. So Azure Databases is sort of this relational database service. A lot of the platform we built on was one of the first services of how we took SQL Server to the cloud. And it provides a sort of a logical relational database for you in terms of storing a set of tables, a set of rows, and everything else you think about a SQL relational database. There's around about 2 million databases running today, around about 1,000 clusters worldwide. The clusters in Azure Databases are about 400 or 500 machines in size. So they're about an order of magnitude bigger than we have for event hubs. And it provides a whole bunch of capabilities. It's a true scaled disaster recovery, full data protection, high scale performance, fully compliant service that can never, ever, ever lose your data. And if it does, bad things happen. And generally, it really, truly has to make sure that people depend upon this thing. So this is kind of takes it to extreme level. Whereas in event hubs, maybe we lose a few messages and people wouldn't complain too much. If I even lost, a row of data inside SQL, things go pretty bad in terms of, let's say, support incidents. And there's 3 flavors of it. And I'm just pointing this out. Don't look at the details too much. Really, the point is that there's a standard version of Azure Databases, and there's a premium version. And the difference is really in terms of the SLA you get inside them all, and in terms of the throughput that you have, in terms of the number of transactions that you can do per second. And the difference actually is that in the standard SKU, you have your database microservices are running, but all of its state actually gets offloaded into remote storage. In the premium SKU, we actually take advantage of replication onto the actual machines that the SQL Server runs on, and does much, much higher performance replication of the database across a set of machines. So we physically take advantage of a direct attached storage, as in just SSDs attached to the machines for where the state gets managed and replicated to, rather than calling off to some remote storage in order for it to do replication. That gives you, there's a huge difference between remote local attached storage and replication to this on the machines you have in the cluster, as opposed to network attached storage. And that's pretty much the difference between standard and premium. If you go off to network attached storage, you have to deal with the additional network latency around all of this. So all of our high throughput services all deal with replication of state and making sure that it's fully consistent state across all of those. So that's what a premium SKU does. It deals with fully consistent replicated state across a set of machines, and it makes sure that there's a quorum of replicas. So if a request comes in, it replicates it to, typically there's 4 replicas of any given database, and any one of those replicas is what acts as the primary for all the reads and writes, and then there are secondary copies of it that are being caught up with at least one guaranteed, and actually in the case of 4, at least 2 guaranteed to be replica copies of the actual primary database, or primary database. So the way the SQL works is they, again, have a set of physical machines. They actually divide these machines, and they're very heterogeneous inside the Azure SQL org. They have a wide variety of different types of machines, from older generations and newer generations that they're for adding. And for them, they typically have, they build these into clusters, and they have what's called a control ring, which I'll talk a little bit about more, which is where all the original requests come into. And then the smallest cluster they have was about 50 machines, but that's kind of that's pretty old now, actually. Most of them are much bigger than that. And so they build these clusters around the physical machines, just like you saw with event hubs. And they have a control ring, basically, where all the requests come into. So this picture probably sort of explains it a little bit better. The concept of an Azure, so you have a concept of a control ring where, again, you have a gateway microservice. Again, all the requests are coming in from the Azure load balancer. They hit this gateway microservice, and it's slightly different in this design because there's a separate cluster that's making the decisions there about authentication and whether you're allowed into the cluster into the first place. And the reason why that's a separate is because the SQL guys are very paranoid about security. And if anyone does a request into the cluster and they trying to break in through the gateway service at the front end and they compromise that service, they live within inside a cluster where there's no one else's data around these things. So the gateway, the service then looks for the cluster, which is where you're trying to find your database. Your database is implemented, again, as a sort of a microservice. And every single one of, if you've ever created an Azure database, it runs as a sort of a microservices app. Actually, it really consists of an app with a number of different services, microservices within inside it all. But generally, there's one SQL server.exe that runs as a microservice that gets deployed inside there. It finds the instance of that inside a particular cluster and where it's running, sends your request to that you want to get an authentication to it all, and returns back to a client an endpoint for you to talk directly to this endpoint database. So you actually sort of skip the control ring once the client has been authenticated about who they can talk to. And so there's n number of these clusters that run in a particular region, and how they effectively scale those out. And they run at pretty high utilization. So of the machines inside there, about 95% of the machine utilization is database capacity, and is highly sensitive to cost optimizations as much as they possibly can. Yeah, if you have a question. Yes. Oh, yes. So the question is if I talk through the gateway, I'm returned a secure endpoint, yes? And that secure endpoint allows me to talk directly to the SQL Server database. That's the way it works, if that's your question. Yes, it's a fully secure endpoint to that database that you've been given access to. So effectively, the design in terms of, this is a microservices forum, is there's a front-end gateway microservice, you have a database, a microservice per customer, you have some metadata service, again, that sort of allows you to think about how to route requests to the particular cluster based upon your incoming requests, and then there's a set of system services that take advantage of some portion of the actual cluster itself, but that's fairly small. And so, typically they have, the hard problems to solve here is that database is a failover unit. There's either the standard SKU just uses remote storage, but the premium SKU has replicated copies of the database across a set of machines, and they're fully consistent replicated copies. So that's kind of the challenge of when the request comes in, you do an operation on the database, we guarantee that at least there's a replica copy that's fully consistent, somewhere else running inside the cluster of machines. So if any given machine fails, the replica copy becomes the primary copy, and then all the new requests are routed to that, including new client requests that occur to the actual database. And again, there's a cost efficiency side of things here, where you know, some databases are massive, some are small. You know, one's, you know, a few gigs in size. You know, one's a, you know, a few tens of gigs in size, and there's a cost optimization packing problem of how is it that I get all my databases, little small ones and large ones, all packed across the machines in this cluster in the most efficient way. And so they report huge numbers of metrics in terms of their utilization, you know, the size of the tables, the amount of memory I'm using, the amount of disk I'm using, the amount of, you know, the actual size of the tables, and then that tells the resource balancing algorithms how best to optimize this over time. And so they're always trying to reduce your hot areas on a cluster. So say someone kicks off a large query on their database, and it takes up a lot of the CPU on that machine. That may cause your database to get moved onto another machine in a shared environment. And then the thing that actually probably is the hardest thing that got solved was, you know, every single one of those databases is a particular instance of a microservice application. Each one of them is unique to any given customer, and each one is independently upgradable and versioned on a particular point in time. So the SQL model is very interesting because what they do now is they build a new feature. They roll it out across a set of customers. So a few years ago, about a year and a half ago, they built a feature called row-level encryption. And you can like encrypt all the data inside a particular row. They went to a set of customers who wanted to try this out. They happened to be a set of financial customers, and they upgraded just their databases to have this new capability. And all the other 2 million databases were left alone. So they can individually upgrade any given database instance. Those people tried out those capabilities. They then upgraded a few more, and eventually over time, they actually, you know, decided that this thing wasn't in preview anymore. And then they rolled out upgrades across all 2 million instances of the databases. So they're doing individual upgrades on a per microservices basis for each of the databases, and they kick off about 10,000 upgrades per database per day, effectively, rolling out new versions for the database code inside those systems, and all of those are run concurrently. At the same time, the underlying machines can be failing, or at the same time, the SQL Azure platform itself can actually be doing host OS upgrades on the actual physical machines. And so you have this coordination exercise where you might have to pause a host OS VM upgrade while you're upgrading all your databases, and then you let those go through before you let the underlying host OS upgrade happen. So all of this makes it sort of fairly complex in the environment. So a lot of it comes down to, how long have I got? Oh, I better start finishing up. I've been keep saying, what is this platform we build things? Actually, are there any questions on SQL at that point? Yeah, well, there's a question in the back there, yes. Oh, well, so the actual number of the actual application that you have as your instance consists of a number of servers. It turns out there's SQL Server.exe microservice. There's actually a logging service. There's actually a backup and restore service, and those are sort of the actual smaller level microservices that make up the overall database application that gets deployed. So they are actually more granular than just that. And you can actually upgrade the individual sort of backup and restore microservice independent of SQL Server.exe as that service, and do those rolling changes if you want. But that collection represents your database, effectively. So there is another level of granularity below what I showed here in terms of the actual microservices that run inside that. And so effectively, so to answer your question, there is a team, for example, that's responsible for the logging service that pushes all the telemetry from any given database to a backend, and they write that as an individual microservice, and they can roll out their logging microservice change inside your database application at any time. And they literally kick it off, and they say, I'm updating the logging service across, you know, the 2 million databases. And there's another team that does sort of the backup and restore service, and they can kick off their one at any time. And all of those get coordinated across them. I mean, that's quite frequent. So you have independent teams building pieces of your database application with smaller microservices inside of all, and they kick off their updates whenever they feel as if they've tested it and it's ready to go. And that's a lot about making this whole thing work. So I've talked a lot about platform. What is the platform this all these built on? Well, back in Azure Databases was the kickoff for creating this platform back in 2009. It proved a lot of the technologies. We built a general purpose platform for the company. We run millions of cores on this platform and launch about 10,000 new cores per day across the company for people spinning up new services, whether they're in Bing or in Azure or in Office. And this platform is called Azure Service Fabric. But the second goal of the platform when we started it all was to have it publicly available. And if you've ever come across this platform and used it all, we released it about 3 years ago. And you can take it and run it on your dev machine. You can run it. It's a hosted service inside Azure, and you can use yourself. You can actually deploy it on premise. And we actually people who take this and run it inside other cloud providers. And so we use Azure Service Fabric for those services inside there that I mentioned, and a bunch of other internal ones as well. So it's kind of the core platform for these, and it provides these capabilities. If you want to know the insane details of how the load balancing algorithm works and what it looks like, there's a detailed paper around the clustering technology in terms of the load balancing technology that we published actually only about a week or so ago after lots of deliberation of just writing the thing, really, more than anything. And actually, the whole platform itself for Service Fabric was open sourced earlier in March. And so you can actually go and see the whole platform. It runs, it's all built in C++, and it runs on both Windows and Linux. And the only version we've actually published so far is the Linux version, strangely. That's mostly because the Windows build system is so ingrained in the rest of this Microsoft build system. Trying to extract that thing is taking us longer than expected. So you can go and build it yourself from the open source repo and get the Linux version of it today. And the Windows version will be there in the next month or so. And then read this paper about what the platform does. And there are 3 versions. You can take the platform and you can run it yourself on your hardware. You can run it on your laptop. All the bugs that exist in the platform exist on your laptop as much as inside Azure. And there's a service that you can build your own services on top of. So all the core services now that build on top of Event Hubs, for example, is built on top of our Azure Service Fabric service inside here. And then we just recently, and that's where you see all these clusters and things like this, how you manage all the clusters, you scale a cluster out. But quite honestly, all the teams inside Microsoft who are building clusters, they have to do cluster capacity management, and they have to learn how to scale their clusters, scale them up, how they have to add new machines. They can put some rules in there, but it's a bit of a painful task. So for the sake of all of just the internal teams, from them going mad about doing cluster capacity management, we've also started to build a fully managed version of this where we, Microsoft, stand up a big cluster of about 10 or 20,000 machines, and then you just build a microservices app itself, which just describes my application, set of services, everything's containerized, and you say, go off and host and run this. And if you want just one container instance running, you can. If you want 10,000 containers running, you can. And everything's just costed around that. And we're trying to encourage more of the teams internally to build on this thing because it saves us support calls when they start talking about 60% of the support calls are about cluster management. So that's the level of pain that happens generally. So there's this thing called Service Fabric Mesh that's coming out. You've got another question.
Yeah, last one, promise.
It's
unfair. Warning, this is an unfair question. You sort of alluded to, quotes, and I'm a CISP, security advanced stuff. And I've got to ask you, Microsoft on average buys 7 companies, security in particular, a week. And you've got what is effectively a universal broker at the front door of your service. How well documented is that? Because you've got to now do all that onboarding with these other services. I'm sure we're all wondering how well GitHub will be running in a year's time on this fabric. How well documented is that interfacing, onboarding, acquisitions process? It's because you're new, and you've been new for 10 years.
You have to repeat your question. Your actual question then is how secure is Microsoft Services?
No. I'll bring a new service in.
Yes.
So here I am. I've got Service X. I'm the world leader in Git.
Yes.
So
yeah.
how am I going to interface, or are you going to use, and it could be any other number services you bought, could be Deus, Microsoft bought that last year.
Yes.
I ran some free training on that, it disappeared. And it's great, you've got some lovely toys, but you've got the universal gateway now. You are the custodian of all that stuff.
Oh, you mean, so when you say universal gateway, you mean we have a set of, Microsoft has a set of services, and how do we do security around them all? Yeah. So I think well, I mean, so each one of these services are independently exposed through an Azure load balancing request. And yes, there are huge numbers of attacks that happen across these services. I'm not really in a position to sort of talk about, I don't know the details. I mean, I just can't answer your question in terms of, how we deal with all of the attacks that happen on these services. But they are frequent and often and very, very diverse, yes. So, yeah, we have a lot of security teams, put it this way. I put these books up here. They're sort of semi-interesting. If you want to pull some of them down, they're free, and they do cover Service Fabric and some other things. And I'll leave those up there inside there. They're pretty good. They do tend to focus on containers from a microservices perspective. As I said, 98% of the services we run don't run in containers. So people get confused thinking that microservices have to be inside containers. They don't. But we do see a trend around that happening quite a bit. If you want to run things inside containers and run it on this platform, you can. But we see a lot of people just run processes and things like this. But those are some useful books around some architecture around certainly how you build applications. And there's some interesting guidance on the microservices patterns. If you can read that URL, I'm afraid, that actually focuses a lot on building microservices and running them inside Kubernetes. But the general principles are very much the same. A lot of the principles around how you run Kubernetes applications. But Kubernetes tends to focus on the infrastructure level. This platform actually takes it to some other pieces inside there that's different from just what Kubernetes does. And if you ever want to try out Service Fabric, there's some resources there for that. I've got time for some questions and everything you can fire at me. Yes?
Sorry, yes, on the remoting side of things, do you have any good repositories of knowledge for that? I mean, everything I know about it is from iDesign, Montgomery.
Yes.
I don't know whether that's very much a very niche kind of view on the way that...
Of how I talk to my service? Are you talking about when you're talking about remoting?
Yeah, I mean, we're looking at putting together a service-oriented architecture. Service Fabric, maybe about 30 different services, or even less than that. It depends on the detailed designers who break that down. But we essentially we just want a calculation engine and scale independently from individual clients.
Yeah, so I think your question is how do you design a service? Well, I mean, there's some general patterns around these things, that points to inside here. But generally, we find that there's two prevailing patterns. Certainly, when you look at Service Fabric, that's like a stateless architecture where you put everything inside an external store. And then there's also a stateful architecture. If you use Service Fabric in particular, they have another capability, which I didn't talk about much this evening, called stateful services, where you can co-locate data. Yeah. And so you have those design patterns. You also have, and how you talk to your service in Service Fabric, if you use that, is any form of communication you want. It doesn't get in the way. The actual platform provides some remoting technologies that you can use out of the box. But if you want to use WCF or you want to use TCP or FTP, you can plug all those sort of in. So we see people use increasingly HTTP requests around these things and building things with Web API around an ASP.NET Core. But I had a gaming company who built their own particular protocol because it had to be very specific to them managing the minimum number of bytes on the wire for the latency around that, built around Signal R around the mechanism. So you can do things like that. Yeah, so it's exactly, well, you want to basically take advantage of existing things that exist already. So, I would take advantage of like HTTP protocols, how you talk to the backend. There's a lot more that still has to happen in the platform itself in terms of how you do communication between services. There's a popular framework called poly.net, which provides circuit breaker, retry mechanisms around all of that. And we're sort of building, I didn't talk about that sort of side of things, but we're building all of that into Service Fabric so you can do intelligent routing between services and things. There's a whole topic. For me, the future direction of a microservices concept, by the way, is I think within 2 years, by the way, no one will be talking about orchestrators. They're just an implementation detail and no one actually cares about the things. And you'll just be talking about how you build, if you're familiar with Istio and that intelligent routing side of things and service mesh, that's really the future direction. Basically, how you just describe an application as a set of resources that has security and identity associated with it, that you can say, go off and run for me, and I know how to get identity of things, and then intelligent routing will happen between services just based on how you define your URL request. And orchestrators and all that sort of thing is just a complete pain that you'll never know about. You need it next week, yeah. And you're not here today. So like 2 years in the future, your life will be easy. But it's always 2 years in the future. Like a PC is always $1,000, isn't it? All right.
Hi there. Basically, you said that Microsoft uses containers there's like a user process rather than a VM, basically a containers. What do you say about processes? What do you mean by that?
No, I was saying, I was saying the majority of services that run on Microsoft don't run inside containers today. The vast majority just run as processes. So if you think about it, you've got a VM, which is this big, yes? And then you've got a container, which is sort of, I don't know, like this big. And then you've got a process, which is sort of this amount of resources. And then, they're just scooping mechanisms around these things. And it, depends on what your objectives are. Containers really are next form of virtualization coupled with resource constraints around the things. But Service Fabric as a platform does resource constraints on just processes. So we can lock it down to like this only has 2 cores and 5 gigs of memory at the process levels. So when you've done that and you already have your executable running, why do you need a container? It just gets in the way, effectively. You don't need that. And then platforms like Service Fabric actually take it to another level where actually a microservice is just a piece of code. And if you just want to launch a piece of code, and you have a process that I could put 10 pieces of code inside your process, and if that process failed and there were 10 microservices inside them all, and I launched them in those pieces of code in other microservices, you get even greater utilization. And that's not used by the SQL guys, just because it gets much harder in terms of opening ports, because they want a port per database. But the Event Hub guys use that a lot because they can pack them in at that level. So there's sort of different choices around these things. I think the future direction is that most things will run in containers within 2 years. I have a bit of a bias about talking about Windows as opposed to Linux. Of course, Windows containers are at least 2 years behind, or 3 years or 4 years behind Linux containers. There's a long way for them to go yet. And so like in 2 years' time, they might have just matured to be useful enough. But that's getting there as well. Anything else? Yes.
You said something about Kafka.
Yes.
Is also built on the same fabric?
No, all I said was Event Hubs.
Event Hubs
Event Hub, as in the product, just released a Kafka head a few weeks ago at Build, so you can treat it just as a Kafka endpoint if you want to do it that way. So they just decided to embrace that endpoint protocol.
Is it like a Cosmos behind the scene you can use? Is it like a Cosmos DB behind the scene you can use any NoSQL?
No. So by the way, Cosmos DB is built on Service Fabric as a thing, but Cosmos DB attempts to have different models on top of the underlying store. So they have MongoDB and Cassandra and their own one, yes? And so Event Hubs are saying like, oh, there's different messaging protocols, and we put a Kafka head on top of that, as well as their own messaging head on top of that, and something those things. So they're just different ways of looking at how you use the same underlying service in terms of how you talk to it. Does that answer your question? So I can basically treat Event Hubs as a Kafka endpoint if I